Thank you very much for this kind introduction and the opportunity to talk about magnetic neutron scattering and polarized neutrons here in the ANBUG online seminar. Why neutrons? That's the most important question for all of us. What justifies that we use neutrons? It's an expensive method. So as you all might know, elastic neutron scattering allows us to determine the precise crystal structure, and inelastic neutron scattering to probe excitations like phonons. But magnetic neutron scattering goes beyond that point. With elastic neutron scattering, we can actually determine the precise spin structure, ferromagnetic, antiferromagnetic, or even more complicated, we can determine the magnetic moments with highest accuracy, and on top the directions of the spins. And that's actually a pretty unique technique. For example, antiferromagnetics, where you have one spin up, one spin down.
Sorry to interrupt, Clemens.
Yeah, Clemens, sorry to interrupt. I think some people think they cannot see the screen shared. So possible we need to share again.
Okay, let me try that.
So can anyone see Clemens' screen? Not yet. Okay, we just wait.
I get the message. The screen can only be seen by the host and co-host.
Okay.
You should have the power to make him a co-host, I think, Teng.
Yeah.
I stop share and
yeah. I have make the Clemens as So how about now? You can share to the people.
Now we're good.
Okay, thanks. Sorry for the technical issues. Okay. So.
Yep. Okay, here we are. Yes, so magnetic neutron scattering, and that's pretty unique. Just think of an antiferromagnet, one spin up, one spin down, and so on. From outside, it does not look magnetic at all. And if you place it in a magnetic field, there is no force acting on it. So how can we prove that this is an antiferromagnet? And this is indeed neutron scattering, the best, if not only technique to do that with great accuracy. On top, inelastic neutron scattering, excitations, magnons. So please forgive me. Some of you might be well experienced people with magnetism background, but I wanted to start really with the basics for those of you who are not quite deep into magnetism theory. So what's the origin of magnetism? And that's actually pretty interesting. We are looking here mainly at transition metal oxides or rare earth elements with partly filled D or F shells, namely here from titanium to copper or praseodymium to terbium. For example, copper in real metal structure is non-magnetic. However, if we remove an electron or two, we can actually have a magnetic moment. So that's for the free electrons. And actually here what happens is, for the D shell, we have in total 10 levels. And now if we have available electrons, we fill it up in the so-called high spin state, 1, 2, 3, all in one direction. That's according to the Hund's rules. And if you add up the spins, you get 1/2, 1, 1.5, 2, 2.5, to 5/2 for the total spin component. So our ions are magnetic. They carry a magnetic spin. Here, the same table, but now we have added the examples, like here copper 2+, titanium or manganite. And you see here, total spin is 2. For copper, total spin is 1/2. The other quantum numbers, L, J, if we calculate the effective magnetic moment, we get values up to 5.9. Actually, that's the comparison with the experimental values, and that works pretty well. It's a pretty good prediction of the single ion total magnetic moment. So most important keyword here is the magnetism is coming from the electrons and not from the magnetic core. So that's the transition metal oxides. For completeness, I also have added the F shell, the rare earth elements. And here, let me just highlight that the spin goes much higher, 3, 3.5, and you can obtain effective magnetic moments of up to 10, which is 2 times higher than for the 3D. In current research, neodymium and praseodymium are really important for soft magnets, for example, electrical cars. If you have a highly efficient permanent magnet, the efficiency of your electrical engine is also tremendously improved. So that's part of current research. Second step is, well, we have free ions now. We know that they carry a spin, but in real life, they are inside a crystal lattice. At high temperatures, the spins are not oriented. That's the so-called paramagnetic phase. So they are pointing in random directions and can actually flip around. Below a certain temperature, the spins order magnetically. And how does that work? Why are they doing that? Because we have various types of interactions which provide a coupling between two neighboring spins. And once again, this is the electrons. It's the electron interaction and not the atomic core, the spin of the atomic core. So the most prominent is the direct exchange, and this is already caused by a simple Coulomb interaction. Already in a hydrogen molecule, you have that term, and it causes actually a parallel or anti-parallel alignment of the spins. That's indicated by the scalar product here. In transition metal oxides, there's an intermediate oxygen ion in between, and that's actually sometimes even stronger than the direct exchange. So in simple words, you have, let's say, an iron here, oxygen, iron. One iron spin can hop onto the oxygen to p orbitals, and on the other side, it kicks out another electron with a spin component down, and that actually motivates an antiferromagnetic coupling. Why are oxides so important? Magnetite, iron 304, is the oldest known magnet, and it's known now already for 3,500 years. Double exchange would be mostly ferromagnetic, and it's mediated by the conduction electrons. And of course, there are many more interactions. The quite important one is the Loshinsky-Moria interaction. And now compare that with the direct exchange. Now we have a cross product here. And that actually means we get a canted spin structure just because of the cross product. Okay, what do we get? We get either ferromagnetic structures or antiferromagnets. In 3 dimensions, the antiferromagnet can actually have different structures. G-type, every spin is in opposite direction. A-type, we have ferromagnetic layers, and the layers are antiferromagnetic. And C-type, we have ferromagnetic chains, and inside in the AB plane, antiferromagnetic structure. But that's not all. I will come to that later on. Canted spin structures or even helical and cyclohedral spin structures are the main interest of current research. Lanthanum manganite as an example, and I picked that because I was amazed that, as you can see here, a neutron diffraction study on manganites 1955. And here a theory model by John Goodenough, 1955. This is actually quite long time ago that people have started looking into lanthanum manganite. John Goodenough, who actually wrote that paper in 1955, I looked up his publications, and he had another paper on lanthanum manganite 2017, so just 5 years ago. He got the Nobel Prize 2019, and unfortunately he died last year. So he was working on these transition metal oxides for almost 60 years. I think that's quite impressive. Lanthanum manganite, the crystal structure is actually shown here. We have edge-sharing MnO6 octahedra. The Mn ions are right in the center, and that's where the spins are located. Here, let me come back again to this third slide. 3D electronic level. We have in total 10 levels. Spin up, spin down, they are degenerate, and we end up with 5 levels. And for Mn3 plus ions, we have 4 electrons available. And now we have to fill them up in the so-called high spin state. So here, if we begin from the left side, we have all the 10 levels. The cubic crystal field of the octahedra split it up into 2 levels, E to G and EG. And the octahedra are not perfect, they are distorted. So we end up, due to that splitting, we end up with 10 levels in total. Now we have our 4 electrons available, and we fill it up in the whole so-called high spin state according to Hund's rules. So we end up with a total spin of 4 times 1/2, total spin of 2. Actually here for completeness is also the shape of the different 3D orbitals. So Mn3 plus free ions, we have a total spin of 2. And below a certain ordering temperature, they now order magnetically in the so-called A-type antiferromagnetic spin structure. That takes place at 140 Kelvin. And at 780 Kelvin, we have a crystallographic phase transition that's shown here in this Neutron diffraction result, splitting into tetragonal order, which indicates also orbital order. So lanthanum manganite, A-type antiferromagnet. So after 60 years of intense research, we can say that lanthanum manganite is well understood. However, the physics of 3D electron systems is not fully understood yet, absolutely not. So important open questions and current research topics are high temperature superconductivity, cuprates, yttrium, barium, copper oxide, or unconventional superconductors, ferrites. Colossal magnetoresistance, very important for applications like in read and write heads. frustrated magnets, we can have competing exchange interaction, and simply spoken, the spin doesn't know what to do in the end. That's called frustration. If you have a spin cycloid, the material might become multiferroic and with a strong ferroelectric coupling. Quantum magnets, quantum critical points is a hot topic in current research. And I will also show you some real results about skyrmions. But before that, let me come back to lanthanum manganite. So that amazing phase diagram from Leutel's group in Augsburg, I call it the most colorful phase diagram, is actually lanthanum manganite doped with strontium, where you remove electrons. And what you end up is with such a rich phase diagram. PM is paramagnetic, FM ferromagnetic, AFM antiferromagnetic, C-type antiferromagnetic, canted magnetic. So a huge variety of different magnetic structures just caused by strontium doping. In addition, some are metallic, some are insulating, and all types of different crystallographic structures. So doping has a tremendous effect on the magnetic structure. So even lanthanum manganite is still interest. Why neutrons? As said, concerning the crystallographic structure, we can precisely determine the type of magnetism, ferro, antiferromagnetic, canted, and even more complicated. And that's really unique technique. We can determine the magnitude of the magnetic moment, and in addition, the precise spin direction. So all together, that's a really unique technique which cannot be provided by standard classical techniques like magnetometry. Where are we doing that? Well, we need a neutron facility. That's an older picture of the Bragg Institute at Lukatz Heights. Someone might realize that Rob Robinson is still standing here in the first row. But most of you have seen that building. That's a picture of the guide hall. And yeah, the two big drums are the small angle neutron scattering setups. And in total, there are two powder diffractometers from Bad Echidna, two XXX spectrometers, a cold and a thermal. We have two neutron reflectometers, Platypus and Spatz. Neutron lower diffraction, the instrument Joey. Actually, the smaller one, I did build that up. Palm of light, strain scanner, neutron backscattering, neutron interferometer, and neutron imaging. So I would say, as compared to other big facilities, we are very well equipped with a real large access to different techniques. But now a bit back to theory. So sorry, the next 2-3 slides might be a bit boring, but I wanted to include that, especially for the experts, to explain why do neutrons interact with the electron spins. Well, we all know how nuclear scattering works. The neutrons collide with the atomic core and scattering takes place, but why with a spin? And the reason is in principle very simple. The neutron itself has its own spin 1/2. Here is the Bohr magneton of the electron, the mu of the electron with the magnetic Bohr magneton. And actually here you see the Bohr magneton contains 1 / mass of the electron. And that answers the question why the spins are so important and not the nucleus, not the core, because the mass of the core is a factor 2000 heavier than the Bohr magneton of the spin of the electron. So the magnetic moment of the nucleus is factor of 2000 and more smaller than the electron spin. So scattering at the spins of the electrons, it's always the electrons. Here the neutron magnetic moment, and to be precise, for quantum mechanics, we have to include the Pauli matrix for the eigenspin values. What happens now? The first term might be familiar. That's basic scattering theory, neutron scattering, derived from Fermi's golden rule. And then the matrix element, the interaction matrix element squared. We have the incoming neutron, and here in addition, the magnetic direction, non-magnetic spin state of the neutron. And here, the initial here, and here the final neutron. In between the interaction potential. So this is the same shape as for nuclear scattering. Let's have a look at the interaction potential. And the interaction potential is the neutron magnetic moment times the vector potential of the electron spin. Looks messy what you see here, I have to admit that. But if we have a closer look, I think all of you should know about that. That's simple classical electromagnetism, simple magnetic dipole interactions, where we have a magnetic dipole here and the spin of the neutron. We have to determine the vector potential of the dipole field of the electrons. And that's nothing else than the simple, no, not simple, but as you should all know from second year, Biot-Savart law. That's the vector potential. From that, we can derive the magnetic field of the electron. Double cross product, note, that's becoming important. So now we have a magnetic field produced by the electron spins inside the crystal. And we have an incoming neutron with its own spin, and that neutron spin interacts with the magnetic field of the electron spins. And if we write down our scattering cross-section again, it's nothing else than the neutron spin here and the magnetic field, double cross product, magnetic field of the electron, double cross product as determined by Biot-Savart law. So looks messy, but once again, it's in principle the well-known neutron scattering cross-section extended by the Biot-Savart law. The neutron spin interacts with the magnetic field created by the electron spins. So sorry for that slide, but I did leave it in for the experts so that you can look it up later on. Now some considerations about that double cross product. I'm not going into detail here, but the main message which we learned from that double cross product is that what we see is the perpendicular component of the total electron spin. So Q would be the momentum transfer by the neutron. That's the direction of the spins inside your crystal. And what we measure in the end is just the perpendicular component. That's what we need to know here. But that's perfect if you have a single crystal on a full circle neutron diffractometer. If you now rotate the crystal in all possible directions and measure the spin component from all Bragg peaks from all the different directions, or one peak, it would be 6 in total, then you can directly calculate the precise spin direction and the magnitude of the magnetic moment. So that's done on a first circle diffractometer or powder diffraction. So here again, I skipped the upper part. Unpolarized neutrons, we have to average over all neutron directions. And in the previous expression, we have quite a number of prefactors. If we summarize all that, we end up with a relatively simple expression. All prefactors combined, and here the perpendicular component to the spin. That's for the free ion. Now we can put it into a single crystal, and we have to add the crystallographic form factor on top. One more consideration. We have also a magnetic form factor. That's coming from the fact that the electron spins are nothing else than a charge cloud, orbitals around the atoms. The most simple orbital is a sphere, and the Fourier transform into K-space gives a decaying function, the magnetic form factor. And actually our Q range here is indeed the Q range where we see the Bragg peaks, because the size of that electron sphere is in the same order of magnitude as the size of the atoms. And that's what we see in diffraction. So the magnetic form factor drops as function of Q, and the Bragg peaks might be here, 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 and here. So we can clearly see that. And that's distinct to the nuclear form factor. Nuclear scattering, crystallographic structures, the Bragg intensity does not drop over Q. Reason is that the nucleus is so much smaller, factor 10,000 smaller, and Fourier transform of that would give a constant intensity. So magnetic form factor drops as function of Q, nuclear form factor does not decrease. Two examples, one-dimensional ferromagnet. Yeah, the spins are located at the atomic positions, it's the electron spins. And in case of ferromagnet, they are all parallel, as shown here, up, up, up. So if you now think about a magnetic unit cell, you see that the nuclear and the magnetic unit cell are identical. So where do the Bragg peak positions are located? They are 2 pi over A, integer values. So we get magnetic Bragg peaks on top of the nuclear Bragg peaks. And now we have that challenge that we need a technique, how can we distinguish between nuclear and magnetic scattering. Antiferromagnet, spin up, down, up, down, up, down. If you want to form a unit cell, you need the identical units, so same repetition rate. And as shown here, the magnetic unit cell is now doubled. It's 2 times the nuclear unit cell. Again, K-space, Bragg diffraction, 2 pi over A. And because we have 2A here, we get 1/2 in the end. And that's now interesting. So we get magnetic Bragg peaks at 1/2 integer positions. So every one of you who is not familiar with magnetic neutron scattering might be puzzled here, but that's where we see the antiferromagnetic Bragg reflections at 1/2 positions. So the challenge now is how can we distinguish between magnetic and nuclear crystallographic neutron scattering? The first trick is the temperature dependence, because above the magnetic ordering temperature, the magnetic signal must disappear. The second trick is we look at the magnetic form factor, which decreases as function of Q. And the third trick is we use polarized neutrons. That's what I will show in the very end. Here's an example from, oops, where are we? Yeah, here an example from one of my projects recently, iron chromium sulfide. The crystal structure is shown in the upper corner. Looks terribly complicated, but it's actually not that bad. This crystal structure is called a spinel, which has edge sharing octahedra and tetrahedra in green and blue. And the centers of the octahedra and the tetrahedra contain iron and chromium. Both are magnetic, have magnetic spins. They order magnetically below 180 Kelvin. And here both the iron and the chromium order simultaneously. Their spins are in opposite direction but parallel. And that's actually called a ferrimagnet. So from outside in a classical magnetometer, it looks like a ferromagnet. But with neutron scattering, you can really separate the iron and the chromium spins. And that's exactly what we have done. Powder neutron diffraction. The upper diffraction pattern is on echidna. The lower one is the contour map of the intensity is obtained on Lombard as a function of temperature. Ferrimagnet, the complication is that the magnetic Bragg peaks are on top of the crystallographic Bragg peaks. So here the very first one is actually both magnetic and nuclear. So how can we now distinguish which fraction is magnetic? Temperature dependence, and that's shown in the lower panel. So here, if you watch again the first Bragg peak, its intensity drops tremendously and disappears at 180 Kelvin. And what's left over at higher temperatures is the nuclear scattering intensity. Actually, if you look at higher Bragg peaks, you also see that, but the effect is significantly weaker, and that's the drop of the magnetic form factor. So what do we learn from these two experiments? The core result is shown here. We determined the precise crystallographic structure and even more, the temperature dependence of the atomic positions. Here is shown the position, the lattice parameter as function of temperature. There's actually a second orbital order transition, which we also nicely see. So high quality, super precise data. From the magnetic Bragg peaks, we managed to extract the magnitude of the magnetic moments, not only the spin directions and type of magnetic order, but also the spin moments, magnetic moments on the chromium and the iron positions. The red curves are actually the Lombard data, and the solid triangles are the echidna data. So here iron 2+ and iron 3+, directly precise magnetic moments. So neutron is really a super powerful technique to determine that. Inelastic neutron scattering. So most of you have heard what a phonon is. Coherent lattice vibration, like a standing wave of oscillating atoms in a lattice. But if we have spins, we can have the same spin standing wave. Actually, here that cartoon is kind of showing that. All spins are rotating simultaneously, like a standing wave. And that's called a spin wave excitation, similar to a magnon, similar to a phonon. Instead of spin wave excitation, you also hear the keyword magnon. Neutrons here is also unique because we can determine the entire magnon dispersion relation in K space. And that allows us directly to determine the strength of the magnetic exchange interaction. So in the beginning, I showed you that there are different types of spin-spin interactions with a quite strange exchange parameter J, which is obviously coming from some weird quantum processes. So like a unknown weird number, but actually here with inelastic Newton sketching, we have a direct trick to measure that directly. If you have the data on your table, you can actually use a ruler and directly measure the exchange interaction. That's really fantastic. How are we doing that? This is an example, yttrium titanate. The black curves are indeed the magnons, the spin wave dispersion. And now I can really take a ruler here and determine that the direct magnetic exchange interaction is about 6 MeV, 5.8. So that's really fantastic. Okay, but back to the puzzle. Sometimes I see 3 peaks in the final spectrum. How do I know that some peaks are magnetic and some peaks are not magnetic, meaning phonons? How can I do that? Again, the 3 tricks, either temperature dependence, magnetic form factor, or polarized neutrons. In that case, we looked at the temperature dependence, and that's shown here. So in the upper corner, the magnetic moments, and that's determined from the magnetic Bragg peaks directly. Magnetic phase transition is at 27 Kelvin. And now we measured a constant energy scan here along that line. And we get 3 peaks, one here, one here, one here. This is the raw data. First peak, second peak, third peak. Now we repeated that measurement at high temperature, 5 Kelvin low temperature, 50 Kelvin high temperature above the magnetic phase transition. And only one of the peaks disappears, the first peak, and that must be the magnon. The other 2 are the acoustic and optical phonon mode. So that's a simple trick, one of the 3 tricks. We applied that here, and I hope that all of you are convinced about that. Finally, in the first hour, I wanted to show you some more exciting spin structures, let's say, results from current research, unconventional spin structures. So I introduced the super exchange interaction where we have J times S dot S. Si and Sj are spins on 2 neighboring atoms. And J is again the magnetic exchange interaction. Scalar product only between parallel spins. The Dialoshinsky-Moria interaction has a cross product. And in real life, that causes a canting of the spins. The first row here shows a zigzag type of spin canting. That's actually pretty common. I have to admit that a perfect parallel spin arrangement is rare. Normally the spins, even in a ferromagnet, are slightly canted. So slight canting is a pretty common spin structure. Okay, but what is if the spin canting would be in one direction only? What we would end up is with a spin cycloid or a spin helix. And that introduces a further symmetry, namely we can have a left-handed or right-handed spin cycloid. The term here is actually pretty funny. It's called time inversion symmetry. Oops, what is that? Are we walking back in time? No, not at all. It refers to the Maxwell equations. And simply spoken, if you look at the third row, if you travel from left to right or from right to left, you get a left-handed or a right-handed spin cycloid. So that's where that interesting keyword time reversal symmetry is coming from. So this right-handed or left-handed spin cycloid, whether you approach from the left side or right side, it's inverted. That's one further symmetry term in your crystal. And actually, multiferroic materials, which allow a direct coupling between magnetism and electric polarization, they are mostly based on spin cycloids. Yeah, well, why is that a hot topic in current research? Just think about a read-write head of your computer hard drive. Now we have direct access to the magnetic structure, and we can detect it directly through the electric polarization, so direct electrical conversion. Or if you have multiferroic hard drive itself, you have 4 bits instead of 2, namely the electrical polarization and the magnetic polarization. If you would use that trick, you could increase your data storage capacity by 5 to 6 orders of magnitude, which means your 1 terabyte hard drive of that size would now contain 100,000 terabytes. That's very attractive for industry, and that's one of the hot topics in research. One example about helical structure, strontium ferrate. That's actually quite interesting because strontium ferrate is isoelectric to lanthanum manganite. It has the same electronic spin configuration, 3 T2G and 1 EG electron, 4 electrons in total, the same as lanthanum manganite. But the main difference is in lanthanum manganite, they are antiferromagnetic, and in strontium ferrite, they are helical. It's a major difference. So how does it look like? What do we get? That's perhaps also new to everyone who never had a look at magnetic scattering before. You get 2 magnetic Bragg peaks at non-integer positions, 0.13 in that case. Not linked to the crystal lattice at all, it's perfectly integer. So what do we learn from that? So the distance here, delta, is directly 2 pi over a. In K-space, the length of 1 full rotation. So the pitch length. So we know exactly how long does it take for 1 spin rotation. And interestingly, these values are not integer values or half or quarter of an integer, so not locked to the lattice. It's really random. The second thing which we learn is the scan is in 1, 1, 1 direction, which means the spin helix is propagating in 1, 1, 1 direction. Last but not least, as you see here directly, that's actually log scale, logarithmic scale. You see how the intensity of the magnetic Bragg peaks disappears. And that's shown here, the integrated intensity, and shows really nice and sharp the magnetic phase transition at about 130 Kelvin. We also looked at the splitting delta here at the Bragg peak position of the magnetic Bragg peaks. And that actually starts to decrease close to the magnetic phase transition. And that's actually funny because what happens is the spin helix expands. And it doesn't appear in steps, it's continuous transition, which again proves that the spin helix is not locked to the lattice at all. It's a real freestanding spin helix independent of the crystal lattice, even so that the spins are located at the atomic positions. I sometimes compare that with a water wave at Kuchi Beach. A water wave is propagating towards the beach. However, if you look at one single water molecule, the only thing which the water molecule does is it moves up and down, up and down. It's not moving towards the beach, but the entire water wave travels. So spins here, the helix, spin helix is not locked to the lattice. Inelastic neutron scattering, that's the spin wave dispersion. Just for completeness, that was measured on XXX neutron instruments, and I'll come back to that picture later. You see now a double U-shaped spin wave dispersion, and the second minima are at the location of the magnetic Bragg peaks. So it's also quite unique spin wave dispersion. Okay, back to spin canting. So once again, spin canting, either zigzag, or if the spin canting is one direction, a spin cycloid or a spin helix. And the most extreme case would be a one-dimensional spin whirl, spin dot. That's actually called a skyrmion, also a hot topic in current research, because it would be also ideal in data storage or quantum computing. Yeah, in 3 dimensions, you could compare it actually with that nicely shaped spin structure where the spins are all pointing outwards. In real life, a skyrmion is really like a magnetic dot where, let's say, 100 spins are combined into one object, and the spin is rotating from up to down, as shown here in this cartoon. The picture next to it is actually electron microscopy, so it's a real microscopy picture, not a cartoon, and you really see the formation of the skyrmions. Once they are formed, they arrange each other in an hexagonal lattice. Let me come back to one single skyrmion. Amazing is if you integrate of the spin density in plane, so-called spin winding number as shown here, you get integer numbers. So the spin density is quantized. So they are quantized objects, they are quantum objects. That's why they were given a name, skyrmion, in analogy to phonon or magnon. They are quantized dots, topological protected quantum dots, and this quantum protection makes them actually pretty stable and robust. If you have a hexagonal lattice, if you do magnetic neutron scattering, you get an hexagonal arrangement of Bragg peaks. And the first person who observed and did prove that was actually the group of Christian Pfleiderer 14 years ago, 15 years ago. Just a side note, Christian Pfleiderer is giving a talk about that from the Munich Research Reactor tonight or this evening here, 7 o'clock Australian time and 11 o'clock German time. So Christian Pfleiderer is currently the director of the Munich Neutron Reactor. So just if you're interested in that. So this is actually video, real life video from our crystals, from our collaborators in Brookhaven National Lab. So it's real time video. And you see nicely the helical phase like zebra stripes and skyrmion phase hexagonal here in between. And what did amaze me most is that everything is fluctuating. So nothing is stable. And here again, the water wave analogon. So skyrmion contains, let's say, 100 spins, but the spins are fixed at atomic positions. But the skyrmion itself can move around, as you can see here. And in between the helix, you sometimes see the formation of a skyrmion, and then it disappears again. Here, just one, that one disappeared. So the entire magnetic system is really wobbly. So it's not that fixed and static as you might think. So there's tremendous dynamics on the seconds time scale. Yeah, that's what we see in neutron diffraction, small angle neutron scattering. This is our data on quokka. If we have a spin helix, the zebra stripe structure, the Fourier transform gives you 2 Bragg peaks. From the position of the Bragg peaks, we can learn the pitch length of the helix and the direction, and of course the magnetic moment. Sometimes we have 4 Bragg peaks, then we have magnetic twins, so 2 zebra stripes. And now in the skyrmion range, sharp 6 peaks. But sometimes they are rotating and fluctuating, and we end up with a ring type structure. So I wanted to show you that in more detail. We have mapped out that phase diagram here on quokka. That's about 9,000 diffraction pattern. And here, as compared to magnetization measurements, squid magnetization measurements. So squid only measures the ferromagnetic component. That's an indirect technique. Neutrons can directly see the skyrmions. So indirect means in the squid magnetometer, we see the ferri or ferromagnetic spin component. And if a ferromagnet, if skyrmions are formed, they kick out, they remove spins from the ferromagnetic chains. So you see a dip in the magnetization measurement. So we don't see the skyrmions directly, we just see a shadow of them. Neutrons, direct technique. And now kind of like a video, raw data measured at 20 millitesla here right through the helical and skyrmion phase. So what you will see is 4 Bragg peaks and higher orders for the helical structure. 4 because we have 2 helical twins, 90° in that case. And then in the skyrmion phase, 6 Bragg peaks or a ring type structure. So let me start that video. So we are starting at low temperature, helical, 4 Bragg peaks and higher orders. Now they disappear, completely gone, and now we see 6 Bragg peaks for the skyrmion phase. So that was a movie of the raw data measured on quokka. So we have something like 1 hour now. The next chapter would be polarized neutrons and how we utilize that. But I would suggest that we have a 10 minutes coffee break or 12 minutes. So my suggestion is we meet again 10 minutes past 11. So what about a coffee break?
So, okay, so hello everyone, we can just have a coffee break and let's start the 11:10. So again, so yeah, waiting for you to come back. So thanks everyone.
Yep, see you then. Bye-bye. Neutrons. So now we talk about polarized neutrons. So once again, neutron scattering is the ideal technique to determine the precise magnetic structure, the type, ferro, antiferro, or canted, the magnitude of the magnetic moments of every individual ion in your crystal, and in the end also the direction of the spins inside your crystal. They could be parallel to the axis or along the body diagonal or even spiral. That's what Newton shows us. A challenge is that we need to find a trick to distinguish between nuclear scattering and magnetic scattering, because as you have seen on a ferromagnet, the magnetic bragg peaks appear on top of the nuclear bragg peaks. And that's sometimes really tricky to distinguish because it could also look like a crystallographic phase transition. So we need to know, is that intensity magnetic or nuclear origin? One trick which I showed you was the temperature dependence, because the magnetic bragg peaks must disappear above the magnetic ordering temperature. The same holds for magnetic excitations, spin waves. Is it a spin wave? Is it a phonon? The second trick is the magnetic form factor, which it decreases for magnetic structures, and nuclear structures, it's constant. Actually, for phonons, it increases with Q squared, just for completeness. So phonons, magnons, the magnons decrease, the phonons increase. And now the last trick, polarized neutrons. So neutrons possess their own spin, but a neutron beam directly from the reactor, the spins are unpolarized, they are random in all directions. But we have a few tricks to polarize, to create polarized neutron beams. And polarized neutron means all the neutrons, all spins of the neutrons are pointing in one direction only. Then they get scattered at a crystal, they interact with the magnetic spins of your crystal. And what happens in an ideal experiment, they get spin flipped. So the scattered neutrons scattered by a magnetic structure are spin flipped. So incoming spin up component, outgoing spin down component. The nuclear bragg peak, here the spins would not interact with the nuclear crystal structure. Nuclear scattering, crystallographic scattering, no spin flip, and polarized neutron scattering, spin flip for the magnetic signal. In real life, it's a tick more complicated, okay, but in an ideal experiment, you can really distinguish here. Okay, for the experts only, sorry, I wanted to include some slides for the experts as well. I've written down here again the full neutron scattering cross-section here, derived from Fermi's golden rule, the interaction matrix, and now I've already excluded the K value and all the prefactors. So what you see here is the incoming neutron spin direction and the outgoing final neutron spin direction. And here the perpendicular component of the electron spin, sigma is actually the Pauli matrix element. Here the form factor of the magnetic unit cell and the well-known delta function, which ensures we get a signal only at the bragg peaks. So let's have a look at that one. So now we should look closer at the spin direction and the direction of the neutron spins, assuming that the neutrons are now all polarized. Ferromagnet, we need an external magnetic field to polarize both the neutron spin or keep them polarized, and also the electron spins in your sample so that we have the incoming neutron beam and the electron spins of your sample parallel to each other. And actually, if we now include the Pauli matrices and really calculate that interaction potential, we get an integer value plus or minus for both incoming neutron spin up and out, or incoming neutron spin down and outgoing neutron spin down. How can we understand that? In simple words, no spin flip has happened. The neutron spin remains up, up, or down, down. So that means in that configuration, we do not get a spin flip. However, if the field is in a general direction, or in ideal case parallel to Q, we get spin flip. So for a ferromagnet, we get actually both components, spin flip or non-spin flip. And now we should choose an ideal experimental arrangement that we mostly see the spin flip configuration. In case of an antiferromagnet, the external magnetic field has no effect at all because from outside, an antiferromagnet is neutral. So now the spin quantization axis is not necessarily parallel. And now we can actually arrange our crystal in such a way that the perpendicular component has no Z component. And in that case, we get 100% spin flip arrangement. Okay, sorry again, that was a bit theoretical for the experts. What's the main message of that calculation, of that consideration? So if we align the sample perfectly in one direction and with respect to an external magnetic field and scattering vector, the magnetic signal appears as spin flip and the nuclear signal as non-spin flip. If you have an arbitrary sample alignment, we get both channels actually partly spin flip and partly non-spin flip for the magnetic signal. So the trick now is we have to align our crystal in an ideal orientation, and then all the magnetic neutron scattering takes place after a spin flip. That's the trick of polarized neutron scattering. I want to show you directly a result here. Let me come back to strontium-4, the helical spin wave dispersion relation. And we had basically two questions here. First of all, is that true? Is that really magnetic? Or is the inner branch a phonon and the outer branch a magnon? And here above 6 MeV, you see something like a continuum. Is that overlap of phonons and magnons, or is it entirely magnetic? So simply spoken, we had no clue. We didn't know at all what it is. We used polarized neutrons, and that's now shown here. Constant energy scans at 2 energy, 6 MeV, here right through that maximum, and 4 MeV through the maximum, 6 MeV through the continuum. Here at the maximum, we see one sharp peak. And now in red color, this is measured in the spin flip channel, and black color is measured in the non-spin flip channel. So non-spin flip channel means nuclear origin. That's where the phonons should appear. And red color, spin flip channel, entirely magnetic signal. So we see immediately there are no phonons, and the entire signal in that color full map is entirely of magnetic origin. at 6 MeV through that continuum. It's a bit more messy, I have to admit. But again, you see black color non-spin flip and red color spin flip magnetic. So that entire signal here is also 100% magnetic origin. So that was a nice trick how to distinguish. Yeah, again, a bit more theoretical. Sorry for that. As said, that's for the experts. But I will focus on the core in the end. How can we produce polarized neutrons? There are a couple of tricks. The first trick is nuclear magnetic interference effect. Simple spoken, for your monochromator crystal, you would use you use a ferromagnet. That's it in short. So, and here again, I wrote down the full scattering cross-section, including the nuclear scattering cross-section, B for the nuclear scattering, and here the magnetic term, including the spin components of the neutron and the crystal spins. If you write it down, you get that final expression. Okay, as said, that's for the expert, and you can actually make a copy of that later on from the video recording or look it up in Squires or Loveday book. So in simple words, you use a ferromagnet, and for the 100 reflection, the signal is spin polarized in one direction only. So that's the trick. You use a ferromagnet, you use the 100 reflection, and your Bragg peak is spin polarized because of the ferromagnetic monochromator. This is how it would look like. This is actually a picture of the Heusler monochromator at IN20 in Grenoble. How that looks like at UNSW, please ask Andrew Manning, and Andrew is actually in the audience. I've seen him or his name popping up. He gave a talk about polarized neutrons, I think 2 years ago. So, okay, what you see here is in the inner core is the Heusler crystal, the ferromagnetic single crystal. To polarize it, we need an external permanent magnet, neodyne iron boride. That's that external magnet. And the internal magnet, that's indeed the Bragg crystal, the monochromator. It's an Heusler alloy. Heusler alloy, copper 2 Mn aluminum. So that can be used on a triple axis. What about another technique using that trick of magnetic monochromator crystals or monochromatic layers? That's actually if you have a guide. You can actually create supermirrors, but magnetic supermirrors. So as you all know, the neutron guide is delivered from the nuclear reactor to most of the instruments at UNSW, Bombard, Echidna, small angle scattering through neutron guides. The neutron guides have supermirrors, which increase the neutron flux on your sample tremendously. And now the trick is you use a ferromagnetic supermirror. And here again, at the reflection, nuclear and magnetic scattering or reflection takes place. And as shown in the cartoon here, only one spin component is reflected. The other spin component of the incoming neutron is transmitted. So reflection takes place only for one spin component. And at the end of your guide, you end up with a perfectly polarized beam. So here are some measured data, reflection measurements on magnetic and non-magnetic films. here, non-magnetic film, the nuclear component. And for the magnetic film, actually here, the interference pattern appears from the thickness of the film, not from the crystal structure. So, and for magnetic films, there's a clear difference between nuclear and between spin up and spin down reflection. So this is actually state-of-the-art supermirror. And in our days, this is all optimized. So you see, important figure is that one. The spin-up component almost stays at 100%, so it's between 80 and 100% up to the 4th scattering order. And the down component, R minus, is almost completely suppressed. So that's the state-of-the-art polarizing supermirror in a neutron guide. That's actually the most elegant and most successful technique to produce polarized neutrons. And the third technique is a helium-3 filter. And that's also operated at UNSW by Andrew Mannings. He is really the expert in that. So if you have more questions about polarizing helium-3 filters, please ask Andrew. He is the expert in that. So what it does is, we all know that we are using helium-3 detectors to detect our neutrons. Neutron gets absorbed, goes into an excited state, helium-4, and after radioactive process, helium-3 and a proton, and that proton is detected in the neutron detector. But on top, you see helium-3 has a nuclear spin. So amazingly, only one spin component gets absorbed and the other one is transmitted. In a helium gas, random orientation, everything is absorbed. But if we have a trick to polarize the helium nuclei parallel in one direction, then absorption takes place only for one neutron spin component. So in simple words, after passing a neutron beam through a helium-3 cell, polarized helium-3 cell, only one neutron spin component is passing through. So, and in order to polarize the helium gas, that's actually done by optical pumping. So a laser is shooting on the helium gas. That creates a metastable quantum state, electronic quantum state of the helium gas. Amazingly, that metastable quantum state has a lifetime of several hours, which allows for the use of that helium cell for something like 12 hours. That's amazing from my point of view as well. You have a quantum state with a lifetime of several hours. It's also quite unique. So helium-3 here is ideal. What we do, we put these helium-3 gas cells, and here are some pictures from UNSW. This is how they look like. The top and front window is silicon, and here inside is the helium-3 gas. And that's actually put into that machine, which is the helium-3 gas polarization station. Main ingredient is the laser, which polarizes the helium-3 gas. And you even see the magnetic coils here. So we polarize the helium-3 gas, then we inside these cells, and then we can transfer these helium gas cells to the individual experimental setups. So, and after 12 hours, we have to replace them and kind of charge them up again. But as I said, it's an intermediate quantum state, lifetime of several hours, so 12 hours, it's pretty convenient. I think the entire setup cost more than $1 million. So here again, more details, Andrew. That's an older list. Andrew, please forgive me. I should have asked you for a current list. This is an older list, how on different instruments at ANSTO polarization is performed. Like here you see Heusler crystal on the inelastic machine, supermirrors, or helium-3 gas cells. So all the three techniques, magnetic supermirrors, magnetic Heusler crystals, or helium-3 polarizers, all the three techniques are used at ANSTO. As said, this is an old list. Andrew certainly has an updated list for that. Now let me explain how the experiment on a XXX instrument works. And I have chosen a XXX spectrometer from Munich to explain that, simply because I did most of my polarized experiments in Munich. So we have an incoming neutron guide directly from the reactor, monochromator, sample, analyzer, second monochromator, the analyzer, and the detector. Both monochromator and analyzer are Heusler crystals, so only one spin component can be reflected. The sample is magnetic, so the nuclear part of the signal will remain spin up, and the magnetic part will make a spin flip. Let's say incoming neutron spin up, spin flip, and now analyzer. If we don't do anything in between, that spin flip component would be completely absorbed by the analyzer, completely eaten up, because the analyzer is also a Heusler crystal and would reflect only the spin up component. So we need a trick here to distinguish, and the trick is, that's not shown in that cartoon, sorry for that, we can place a spin flipper into that field. A spin flipper is a high frequency electromagnetic field, and if tuned directly, you get a resonance with the neutron spin, which flips the spin up again. So now what happens for magnetic scattering? Unpolarized incoming neutron beam, Heusler crystal, only one spin up component. The sample magnetic signal makes a spin flip down. The outgoing, the scattered neutron passes through the spin flipper and is flipped up again. And now the second Heusler crystal detects that step-in component. So the trick to distinguish is that we place a spin flipper in between. And now spin flipper on means spin flip, means magnetic signal. Spin flipper off means no spin flip, means nuclear signal, nuclear break peaks. So this is how it works in a real experiment. Some additional information for really doing that experiment is what you see here are these big boxes, and actually to keep the neutron polarization during their flight, there's a guide field, magnetic field to keep them polarized. In Munich, it's a bit more complicated because you can even rotate the spin direction and perform so-called spin echo polarized neutrons. So you learn additional information like ultra-high resolution neutron, inelastic neutron scattering with that spin echo technique. So in Munich, it's even more sophisticated. But yeah, what we need for all the instruments, Taipan, for example, we need a guide field to keep the neutrons in one direction only. The spin flipper sounds super complicated, but actually it's really just a high frequency electromagnetic field, and to initialize that, to calibrate that, we do that directly live in action at the neutron beam. So we simply detect the spin-up component and the spin-down component separately and tune the magnetic field to achieve a maximum in both. So that alignment is sounds super complicated, but in the end, it's a thing of 10, 15 minutes to record that. So that's polarized neutrons. Yeah, where's the bottleneck with polarized neutrons? Sounds like a fantastic technique, and indeed it is. Why isn't it used every day? The problem is that all these polarizers, Häusler crystal, helium-3 cell, eat up quite a large amount of neutrons. So at least 50% for one spin component only, but in real life even more. So which means you need significantly more neutron beam time to perform such an experiment. That's the experimental disadvantage. The advantage is the results are perfect. So you know exactly magnetic or not magnetic. Another example, so that was XXX. And actually here back again, so that's just what you would get on a XXX instrument. Neutron reflection. This is a sketch of Platypus at UNSW, the neutron reflectometer. The incident beam is a polarizing supermirror, a magnetic supermirror, which means the incoming neutrons are already spin polarized. That's absolute perfect to use. And the analyzer actually also would detect polarized neutrons, and we have high frequency spin flippers before and after the sample. And here would be the sample location in ideal case in an external magnet. So we have a polarized incident beam and we have two spin polarizers. And that's what we get. So again, neutron reflection is ideal to determine properties of thin films, not only the chemical composition, but also, let's say, surface roughness, or if there's some chemical interpenetration. Perfect ideal technique. And now, if we use, as shown here, spin up, spin flipper position, or spin down, spin flipper position, we can see the magnetic structure in the film. So that's an example from my own research. Strontium titanate substrate, lanthanum strontium manganite as film. And that's the material which I explained in the beginning. In that case, it's ferromagnetic. And on top, bismuth ferrite, which is a multiferroic. And we wanted to know, this is the actually ideal Brown film geometry, but we wanted to know how sharp is the transition from lanthanum strontium manganite to bismuth ferrite. The idea here was, can we manipulate the cycloidal spin structure in bismuth ferrite through the lanthanum strontium manganite ferromagnetic structure, and therefore we would need an intermediate layer, magnetic layer, not crystallographic magnetic layer to enhance that interaction. So we did the experiments. This is the raw data, and you nicely see the difference between the two components, spin up, up, or spin down, down. The difference, normalized difference, is plotted here again. So green data are really that asymmetry. And now we applied a model in order to determine, and the result is shown here. What we obtained is indeed an almost 30 angstrom thick intermediate interface, magnetic interface here in that depleted magnetic layer. So that was an important result. So that was measured on platypus at UNSW. And sorry, I would like to show that picture as well. That's the same sample here at 300 Kelvin and now at 150 Kelvin, but measured in Munich at NREX at the FRM2 research reactor in Munich. So sorry, I had to make that comparison to show to a broader neutron community that there's quite a number of these instruments worldwide. The data quality is, by the way, absolutely identical. In Munich, we have more data points because we had more beam time, but the data quality is identical. Yeah. So, and yeah, sorry, I'm already coming to the end of that presentation. So let me summarize. So neutron scattering is really the ideal technique to determine the precise crystallographic structure or orbital order. That's what all of you know. I hope I have convinced you that neutron scattering is also ideal and perhaps unique to determine the precise magnetic structure, not only that there is a magnetic moment, but the type of magnetism, the magnetic moment on each individual ion, and the spin direction. Inelastic neutron scattering, phonons or magnons, spin wave excitations, spin gaps, and strength of the exchange interaction. And as said, the challenge is how can we distinguish between nuclear and magnetic? Trick number one is temperature dependence. Magnetic signal disappears above the magnetic phase transition, magnetic form factor, which drops, or polarized neutrons, which is available at UNSW. I have a list here of references of textbooks. So most of you might know some of these resources already, but I still have listed all of them. So if you want to learn more about magnetism, solid state magnetism, F. Croft Mermin, O'Cowley, Cambridge. Neil Ashcroft is actually from New Zealand, and whenever there's a Wagga Wagga conference and when he visits home in New Zealand, he joins the Wagga Wagga conference. So just a side note. Squires, Lovesay, and also a good book on XXX, neutron scattering, Gen Shapiro, Gen Shirane, Stephen Shapiro, and John Tranquada. So, yeah, and let me finish the talk with that skyrmion overview, our QUOCA results on skyrmions.
Thanks, Clemens. That's really impressive talk, and this is a really beautiful image. Yeah. So, okay. So then we pop up to the Q&A session. So any questions, you can just raise hand, or you can pop up in the Q&A session part or the chart part. So I think the polarized neutron is very powerful, and thanks for Clemens to give some, and also Andrew to give some updated information related to that. So currently, could we do the diffraction by using the polarized neutron?
That's a question to Andrew. I know that they have curved helium cell, but I don't know the current status. So Andrew, perhaps if you are still here, please. Is Andrew still around?
Yeah, so Andrew said that can do the one byte. Can do on one byte. Yeah.
So I know that they have purchased a curved helium-3 cell to cover the entire diffraction pattern, but I haven't used it yet. So
Yeah. Yeah. That's great. Great to know this capability. So yeah, I got another question related to the skyrmion. So after collecting this kind of fantastic patterns, how can we transfer back to the real space?
Yeah, in real space, the size of a skyrmion is 50 to 100 nanometer. So it's a pretty large object, actually, and that's why we need small angle neutron scattering to detect that signal. So if we would measure that crystal on koala or powder on wombat echidna, we would not see that splitting here at all. So in real life, the skyrmions are rather large objects. And concerning technological applications, you can even separate a skyrmion as a single independent object and move it in a wire, for example. So there are a couple of tricks how you can separate skyrmions and then use one skyrmion as, let's say, one data bit in computer data storage applications. And that data bit skyrmion would be still much smaller than the domain walls in a current computer hard drive. There must be a certain spacing between the domain walls, otherwise the magnetic bits depolarize each other. And the skyrmion is much smaller in size, so it would increase the data storage capacity tremendously.
Okay, thanks. Any other question? So if no questions, let's thanks Clemens again for this fantastic talk. Yeah, thanks Clemens. And another thing is that we also will have other lectures in future. So just keep receiving our updated information from the ANBUG and also the ANBUG website. Okay, thanks for everyone to attend today's event. Yes, thanks again for Clemens' impressive talk. Okay, see you.
See you. Bye.
Yeah, bye bye everyone.